James. I'm Senior Research Fellow in Translational Sciences in Bristol Medical School. As the department maybe suggests, I'm not an AI expert. I come more from the clinical biomedical side. And I think I'm one of the people in this field who's getting very excited about the opportunities that AI can be used to really boost some of the effectiveness of what we're trying to do in the medical sciences. So specifically, I work in the field of tissue engineering, regenerative medicine. Basically, what we do is we grow parts of the human body. We do this via cells, materials, and chemicals. We use these in different combinations. We take inspiration from nature, typically. And the end result, what we hope to have, is a tissue, a living tissue, which replicates a lot of the structural and functional complexity that you see in tissues such as bone or skin or heart or whatnot. And this obviously has very clear clinical applications, so we can use this as restorative grafts, but we can also use this as models. So we can use this as a way of understanding different elements of growth, and, health and disease and drug efficacy. So in this sort of workflow, we have clear opportunities for AI to integrate and improve what we're doing. Cells across different people, the people in this audience, everybody will have different cells which have huge amounts of information stored in them in terms of their genomic profiles. This is large data sets. And the materials and the growth factors, we can use all sorts of different combinations, all sorts of different parameters here. And it's simply too much, really, for an individual or a team to work on this and to understand how this very large parameter space can be used to influence how a tissue grows and performs. And that's really what we want to do. We want to be able to say for a person's particular cells, are those cells going to respond to a cancer therapy? Or how can we optimize the materials and the growth factors to produce the very best tissue constructs? So that's really my excitement in this area. I'm very new to this, and I'm very grateful to the Gene Golding Institute for funding one particular research project, which I'm going to talk to you today about, and this is concerning the human brain. So we are very interested in this organ. It's the most complex structure, I think, in the known universe, but it's also very inaccessible. We cannot interface with this very easily. So how do we get around this puzzle of how to study the human brain? The answer has maybe been given by some very interesting developments in the biomedical field over the last 10 years. We are now able to grow these very complex structures, which we call brain organoids. These are multicellular, so they have lots of different cell types that you would naturally find in the brain, and they're organized into these 3D structures, and you have these different regions which replicate the different regions of the brain. So these are now being very widely explored as proxies to understand, for example, the development of human brains, Zika virus interactions, encephalitis, these kinds of challenges which you couldn't ethically do with a human. So we're very interested in this model. A very well-established limitation of this is its unpredictability, however. So we can have a system like this where we have, from over the course of 10 days, we have a ball of cells and they're producing this organoid. And we can also have a situation like this where we have something which is completely different. And this is really, this is not helpful. If we're wanting to look at the effect of particular genes or particular drugs upon the development of the brain, we need to have a very standardized baseline. And at the moment, it's not really very well understood why this happens and why you have this unpredictability. So what we're doing is we are looking at monitoring this process over a period of time. And if you work with these organoid systems, if you grow these regularly, you kind of get a little bit of an intuition. You might be able to say at day 10 I think this one is going to grow a little bit like this, or I think this one is going to grow a little bit like this. It's a little bit like the mole situation that we were seeing a couple of talks ago. Clinicians will be able to determine, based on the morphology of the mole, whether it might be cancerous. We can do similar here. But this is very intuition, human-based, it's very biased. So what we're looking to do is put together an AI framework to be able to understand this and really unpick this in detail. So I haven't, one issue with this is that we generate very large amounts of data, so I haven't actually got all the data to show you today, but basically we've been producing these screens here. We've generated nearly 200 of these organoids, and we've mapped this over time. And over the course of the project, we are looking to expand this massively, so nearly 800 organoids. And this should provide these timelines and this large data set to then be able to unpick those early signatures and to be able to understand how the morphology of these early structures, how they lead to different development patterns in the brain. And by doing that and linking this with biological information, we hope to be able to gain new insights into how the human brain develops. So just all that remains to say is thank you to the people involved. So Aya and Carolina, who have been growing the organoids, and Sammy on the right there, who's been processing the data, and also the people who've been working with us on the machine learning side of things. So thank you very much.